Okay, so we looked at a function. Actually, we looked at a couple of functions last time, but one of them in particular was this one. I think it was equal to on this side. I'm going to say it is anyway, and not equal to on that side. And this was 1, and this was -1. And this was a function that I drew on the board. And I asked, what is the limit as x approaches 0, right? What is the limit as x approaches 0 of this function? And this was, I think we defined it as f of x equals 1 if x is greater than or equal to 0, and -1 if x is less than 0. All right. And we determined that this limit doesn't exist. Because when I approach 0 from the right along this path, I go to 1. And when I approach along this path from the left, I go to -1. And those values aren't the same. Right? So the notation that we use for that is that little plus or minus after the number. Okay? All right, so the limit, let's see, I'll start on the left. So a left-handed limit we write this way. The limit as x goes to a with a little minus sign in the corner of f of x equals L. A right-handed limit we write as the limit as x goes to a with a little plus in the corner of f of x. I'm going to say m because they don't have to be equal. Okay. All right, so that's what that notation means, and that's what we're going to talk about today. All right, so what that does is it gives us a measure of, or a way to write out a definition for when a limit exists. Right, so the limit, I'll get back to my, well, actually, let me do this first before I do that. So the left-handed limit here would be the limit as x goes to 0 from the left of f for this function, right? Coming along the left would be -1. The limit as x goes to 0 from the right of 0, again, coming in along this path would be +1. All right, because those two are not the same, we said that limit didn't exist. All right, and I didn't make that formal last time. I'm going to make it formal now. All right, so we say that the limit as x goes to a of f of x exists provided the limit from the left of f of x is equal to the limit from the right of f of x. If those two are the same, then the limit exists. Okay. All right. Now we can, all right, so there's a little theorem box on page 122 in your book, if you're interested, that states that. Okay. So when you look at a function and you want to determine whether the limit exists, so there's a nice little example here that we did. All right, this is another one that we did in class the other day, which was f of x is negative x if x is less than or equal to 0, and it's equal to the square root of x if x is greater than 0. All right, so I want to find, right, so now what is the limit as x approaches 0 of f of x? Does it exist? If it exists, what is it? All right, well, we test the limit as x goes to 0 from the left of f of x. All right, well, from the left of 0 is x less than 0, so that's this part of the function up here. So that's going to be the limit as x approaches 0 from the left of negative x. Right, and if I put 0 in there, what am I going to get? I'm going to get 0. I take the limit as x goes to 0 from the right of f. From the right, our value is greater than 0, so that's this function right here. So that's going to be the limit as x goes to 0 from the right of the square root of x. All right, and if I put 0 in there, I get 0. Right, those two are equal. Oh, I'll write an equal sign that way. All right, so that means that the limit as x goes to 0 of f exists, and it's equal to 0. All right, so yesterday I did that with the graphs. Today I'm doing it algebraically. Okay, I'm in the right place. All right, now we can extend this concept of a limit existing to define or determine whether a graph has a hole in it. All right, a hole or a break or something that prevents the graph from being continuous. Right, so when we look at, go back here, when we look at this function here, all right, this break in the graph, the fact that it jumps from here to here, is what's called a discontinuity. All right, it's a place where the graph fails to be continuous. If we look at this function here, it's the same type of piecewise function. The difference is that, let's see, can I make that meet up and see? Yeah, there we go. That looks like that. All right, so this one is continuous. All right, there's no breaks and there's no holes. So anything that causes a break in the graph or a hole in the graph is what's called a discontinuity. And we can define the property of a function being continuous based on limits. All right, so let's take this one as our example, right? Based on limits, yeah, that's what I said, wasn't it? So right here is the point where if there was a hole or a break, there would be one, right? That 0 where this splits. Because there's no break there, right? And there's no hole there, that means that function is continuous. All right, so what we need for a function to be continuous. Oh, okay. Don't worry about it. That's why I record this. All right, so f is continuous provided Wait, hang on, because we don't talk about continuity without talking about continuity at a point. So get rid of that. Come on. Without talking about continuity at a point. F is continuous at x equals a, provided the limit as x goes to a from the left of f is equal to the limit as x goes to a from the right of f. That is, the limit exists and it equals the value of the function there. All right, so if we add the condition to our definition of the limit that the value of the function is the same as the limit, then we have a continuous function. All right, so let's take a look at some examples of this. All right, and let's see how far we get today. All right, so let's see, what do I want to do first? Let's do something really simple first. Let's take f of x to equal x plus 2. All right. Now, these questions are in the homework are, oops, hang on. My mouse was on the wrong screen. All right, let's check, is this continuous at x equals 1? All right, so we'll start off with something like this. Okay. All right, so what do I have to do? Well, I have to satisfy this definition. All right, so I have to have the limit as x goes to 1 exist. So that means I check from the left. All right, well, this is just a linear function. So as x approaches 1 from the left, this is going to approach 3. I check the limit as x approaches 1 from the right. All right, well, again, this is just a linear function. So as I approach 1 from the right, this is going to be approaching 3. And then what is f of 1? Well, that's 3. All right, so all 3 of those are satisfied. So this function is continuous at 2. In fact, because it's a polynomial, polynomials are continuous everywhere. All right, so when you see a polynomial function, if you're asked to find any points where the function is not continuous, right, polynomial functions are continuous everywhere. Let's go for something a little more. How about this? How about we take g of x and we make it x squared minus 4 over x minus 2. And this time I want to know, where is g not continuous? Okay. Where is g not continuous? All right, well, it's a rational function. So it's definitely going to have a discontinuity, some kind of discontinuity anywhere where the denominator is 0. So if I take the denominator out, set it equal to 0, I get x equals 2. All right, so I have a possible discontinuity at x equals 2. I need to test the limit from the left and the limit from the right, and then show that the function is not defined there or defined as something different. All right, now because this is a rational function, before I take the limit, I have to reduce the fraction. All right, so g of x squared minus 4, x minus 2, x plus 2, over x minus 2. All right, so that's going to be x plus 2, where x is not 2. All right, so now if I take the limit as x goes to 2 from the left of g of x, all right, that means I'm approaching 2 from the left here. So that's going to approach 4. If I take the limit as x goes to 2 from the right of g of x, again, as I approach from the right to 2, this again is going to approach 4. So the limit actually exists here. The problem that we have is f of 2 does not exist. Right? Does not exist. Okay, so this also allows us to figure out what kind of discontinuity I have. All right, when your limit exists, but your function does or is equal to something else, you have a hole. All right, so this represents not that kind of hole, the other kind of hole. This represents a hole at x equals 2. All right. Let me see. I'm just looking for another. All right, let's do another one. Let's take h of x equals x plus 2 if x is not equal to 2, and 1 if x is equal to 2. Okay. Actually, you know what? I want to change this one. I don't want to use, because I just did one exactly like this. Let me change this one a little bit. Let's make this x plus 2 if x is greater than or equal to 2, and 1 if x is less than 2. Okay. Yeah, that'll work. All right, so if you're asked, again, are there any places, any values of x for which h is discontinuous? Okay. Now, when you see a piecewise function like this, all right, this is very common, all right? When you see a piecewise function like this, and you're asked to find any discontinuities, those discontinuities are going to happen, if they happen, at the breakpoint. All right, so I'm going to look up here and say, what's the breakpoint? Well, the breakpoint is x is 2, right? That's where I go from this function to this function. So possible would be x equals 2. All right, so that's what I would want to test. All right, so I'm going to check the limit as x goes to 2 from the left of h. So from the left are values less than 2. So that is the bottom function. So that's 1. And, well, 1 is a constant, so that's just going to be 1. The limit as x goes to 2 from the right, right? Well, from the right is values greater than 2. So that's this function up here. That's going to be x plus 2. That's going to be 4. All right, so I crash and burn here right away. All right, I don't have to check the value of the function because the limit itself doesn't exist. All right, so the limit as x goes to 2 of f does not exist. All right, so right there, I have a discontinuity. All right, now the type of discontinuity. You can have a hole, which we saw in the last example. You can have a break, which is what this is. All right, so this, the limit not existing here, indicates a break in the function. And if I were to do just a quick, if I was to do just a quick sketch, all right, for values less than 2, all right, so let's put 2 in here. Here's 2. For values less than 2, the function's equal to 1. So we'll say 1, 2. Actually, I need to go all the way up to 4, don't I? All right, so for values less than 2, it's not equal to there, the function's equal to 1. Okay. For values greater than 2, the function's equal to x plus 2. So that would put at 2, that would put the function up here at 4. That's filled in because it's equal. And I'm just going to do that because it's a positive slope. All right, so the fact that the limit goes to 2 different values, one on the left and one on the right, is an indication that you have a break in the function. All right, so the only other type of discontinuity would be a vertical asymptote. And you're really only going to get a vertical asymptote where you have a legitimate rational function where the denominator is 0. Okay. All right. So where are we here? Okay, so properties of continuous functions. All right, let's see. What can we do here? Let me, because I'm having issues with, come on, turn on. Oh, I got to turn that off. No? Oh, wait, I did it again. All right, because I have it labeled differently here. Hang on. Need to be up there. All right, so let's take a look at this real quick, just so I don't have to write it all down. All right, properties of continuous functions. The constant function is continuous everywhere. The identity function is continuous everywhere. All right? Now, if f and g are continuous at a point, then the power function is going to be continuous at that point. Sum and difference is going to be continuous at that point. The product is going to be continuous at that point. The quotient will be continuous at that point, provided g of a is not 0. Okay? So you get continuity extending everywhere you want it. Okay? Polynomial functions are continuous everywhere. Rational functions are continuous everywhere except where the denominator is 0. All right, so if you look at the 3 functions right down here at the bottom, all right, f is a polynomial. All right, find values of x for which each function is continuous. All right, so f is a polynomial, so it is going to be continuous everywhere. G is a rational function. So a rational function is continuous everywhere except where the denominator is 0. Well, the denominator here is x squared plus 1, so it's never 0. Right? So this is also continuous everywhere. C is a rational function, but there are 2 points where the denominator is 0. All right, so this will be continuous everywhere except x equals 2 and x equals 1. All right, don't worry about how I got that. Just those 2 values are eliminated. Take the denominator out, set it equal to 0, and solve it. Okay. All right, so you can use the properties up here to you can use these properties up here separate of the definition. If you know you have a polynomial, a rational function, anything like that. All right, if you find points that you think are going to be discontinuities, let's see if they do it. They don't. Okay. If you find points where you think they're going to be discontinuities, all right, you're going to want to go to the definition and do something like this to show that they're not continuous. All right, for rational functions, it's not that big a deal because zeros in the denominator are vertical asymptotes, and vertical asymptotes are discontinuities. All right. Okay. I was really hoping my physical switcher would work. I wasn't anticipating. I was not anticipating Firefox having hotkeys where I had hotkeys. Okay. Another consequence of continuity. All right, continuous functions. If we know a function is continuous everywhere, then there are things we can tell about that function. All right, one of the things is what's called the Intermediate Value Theorem. All right, and the Intermediate Value Theorem, you know what, I'm just going to, rather than trying to redraw this on my whiteboard, I'm just going to come back here and use the purple box, okay? All right, so the Intermediate Value Theorem says if f is a continuous function on a closed interval, a, b, and m is any number between f of a and f of b, then there's at least one number c in the interval from a to b such that f of c is m. Take a look at these pictures here. All right, in fact, I'll even make them bigger. I'll make them bigger and then move them over to make them easier to see. Okay, take a look at the pictures here. Okay, we have a closed interval from a to b, and we have a curve that's defined on that interval, and it's continuous on that interval. All right, if you take any value between f of a and f of b, I can project it back to the curve and down to find that value c, such that if I take f of c, I get my m back. Okay, that is a consequence of this curve being continuous. All right, now that may seem in and of itself to be kind of an odd thing to think about, but let's think about it in a more specific way. All right, if instead of just an arbitrary value, I am specifically interested in finding a zero, a root. All right, what that does is I can use the x-axis as my, all right, this is y equals 0 here. All right, and what the theorem says is if I have a continuous function on a closed interval, so here's a and here's b, and I have, let's say, f of a up here and f of b down here, that somewhere in between a and b, the function has to cross the x-axis, right? So if I have f of a up here somewhere, and I have f of b down here, there's no way to get from here to here without the function crossing the x-axis. So that somewhere in between, I have a c such that f of c is 0. That is, the equation or the function has a root. All right, that's extremely helpful. It may also seem extremely obvious. All right, but it is a consequence of a function being continuous. If you didn't know that the function was continuous, you couldn't make the assumption that you have a 0 between a and c just because the function jumps from being positive to negative or negative to positive. All right, but because we know that function is continuous, it has no breaks and no holes, the only way it gets from f of a to f of b is to cross the x-axis. So this gives us a way to find or to determine whether or not a function has a zero on an interval. Okay, so let's take a look at an example. All right, so suppose I have this. F of x is x to the third plus x plus 1. All right, so first of all, you need to know that that's continuous for all values of x. All right, so I want to know, does this have a 0? Okay, so does this have a 0? Let's see, does this have a 0? F have a 0 on the interval from -1 to 1. All right, so does this cross the x-axis between -1 and 1? All right, well, the first thing I need to know is that f is continuous. All right, so f is a polynomial. And is continuous everywhere. All right, that's one of the properties of continuous functions, is that polynomials are continuous everywhere. All right, so I know I have a continuous function. So now the only other thing I need to show is that one end of this interval is positive and the other end is negative. I don't care which is which. I just have to know that the function changes signs somewhere in that interval. All right, so f of -1. All right, so it's -1 to the third plus -1 plus 1. All right, so it's going to be -1 plus -1 is -2 plus 1 is -1. All right, so that's less than 0. The other endpoint, f of 1, that's 1 to the third plus 1 plus 1. So that's 1 plus 1 plus 1, that's 3. That's greater than 0. All right, so I know that f of -1 is less than 0. Right? F of -1 is less than 0, and f of 1 is greater than 0, and f is continuous. Therefore, by the way, you write therefore in math like this, okay, without the parentheses. All right, so therefore, by the intermediate value theorem, also, by the way, we tend to say IVT, the intermediate value theorem, f has a 0, 0, 0 on the open interval from -1 to 1. Okay. All right, this is the first time we're doing any kind of mathematical proof. Okay. This is technically a proof. All right, we're proving that f has a 0 in the interval from -1 to 1. All right, now you may need to, I'm just looking at, let me just look at the homework problems real quick for 1 second here. And let me see. I can't find them. Maybe they're further down. Here we go. Use the intermediate value theorem. No, they give you the interval for each one. Okay. What are the 3 times? Okay, never mind. Let me take that out. I'm going to show you some math language here. All right, so the homework does give you the interval. That's what I was checking there. When you're writing out math, there's like a shorthand. There's like a math shorthand. All right, and those 3 dots, that, like that, means therefore. All right, so when you're writing out a little mathematical proof and you're ready to state your conclusion, you say, therefore, this is true because of this. Okay. How would it look if it has no 0? Okay. You can't prove a negative. Okay. So you can't prove that something has no 0. I mean, short of graphing it and looking at the graph, you can't necessarily prove that something has no 0, because the way the theorem is stated, all right, how can I say this without completely confusing you? The function would probably fail to be continuous, or it would fail to change signs. Just because it doesn't change signs, you can't conclude that there's no 0. You can only conclude that the conditions for the theorem are not satisfied. All right, because, here, look at this. All right, suppose I have a function, and I'm going to end on this. All right, so here's A, here is B. Suppose I have a function that does this. Okay, and here is f of B, and here is f of A. All right, f of B and f of A are not going to change signs here. That does not let you conclude that there are no zeros. All right, because that could happen that way, or it could happen this way, right? It just stays above. The thing is, if it doesn't change signs, you don't know anything. Right? You actually know less. So you have to be careful when you're going through a problem like this. All right, you need to first verify that the conditions for the theorem are satisfied, and that's what I'm doing up here. All right, the conditions for the theorem have to be satisfied before, actually up here, all right, before you can draw a conclusion. If the conditions for the theorem are not satisfied, you cannot draw a conclusion. Okay. There are only 2 problems on the homework, and there is 1 problem on the test. Okay, there's 2 problems on the homework, 75 and 77. All right, that ask you to do this, but 75 through 78 are all problems that involve doing this. I'm pretty sure they all work too. Okay. All right, so in order to show that a function has a 0 on an interval, the conditions for the intermediate value theorem have to be satisfied. That is, that your function is continuous on that interval, and that the endpoints change sign. One is positive and one is negative. If either of those fail to be true, you can't proceed with the problem, all right? You can't draw a conclusion.